Welcome back to part two for this week. So, we'll finish up with a couple more sections here, and then next week we'll pick it up from 5.4, which is around the central limit theorem and the sampling distribution stuff. All right. So, the next two sections are fairly straightforward. That's just basically the application of whatever we covered in the first lecture for the week. So, a bunch of different examples on how to use what we've learned so far, and then we'll stop for the week. Okay. So the first thing is that how do we use normal distributions for finding probabilities, right? So the end goal at the end of the day is to calculate probabilities, and we if we have a normal distribution, if we have a continuous random variable which exhibits in a normal distribution, how do we find probabilities, right? That's what we're going to try and do. Okay. So suppose we start with an example, right? So we have a random variable x. We know it's normally distributed, and we can find the probability that x will be in any given interval. That's the goal, right? So suppose we want to find if this is the normal variable x. It's a continuous. Let me get a pen here. It's a continuous random variable x here, which is distributed like this, right? So the mean is 500. The standard deviation is 100. Again, it's bivariate, so we need both things. We need the mean, which tells us the center of the distribution, the standard deviation, which tells us how the distribution spread. Okay. So this is the distribution where the mean is located at 500 and the standard deviation is 100. Okay. So the question is, what is the probability that x will take a value which is less than 600? Okay, so the value of 600 is here, right? So this is the value of 600. What is the probability that x will take a value which is less than 600? So to answer that question, if this is 600, the probability that x will take a value of 600 is the probability that x will take this value, the probability that x will take this value, this value, this value, and so on, all the values which are lower than 600, which is to say it is asking the question, what is the area to the left of 600 on this distribution? Okay, so the question then is, how do I find this area? Okay, so one thing is that, okay, I can't find the area directly for this normal distribution. So what my trick is to basically convert it into its relevant z-score and then use the standard normal table to find the area. Okay, so how do I do that? So I'm interested in the value of 600. So the z-score here is the value itself. So 600, that's x, that's the value I'm converting or transforming. This is the mu is the mean, which is 500, and the standard deviation is 100. So 600 minus 500 over 100, that's 1. That tells me that the z-score, the relevant z value that I need to look up in the standard normal table is 1, right? So probability that x is less than 600 is the same as the probability that z is less than 1, okay? How do I find, so these two areas are basically the same. So I can go into my standard normal table, look up a value of 1 and look at the area which is associated with it. And now I would know the value, this probability that x is less than 600. Okay. So let's apply this, right? So let's apply this in this real world data. So a survey indicates that people use their cell phones on average. So the average, so we know the mean is 1.5 years before buying a new one. So we know what the average usage duration is, and we know that the standard deviation is 0.25. Okay. A cell phone user is selected at random. Okay, find the probability that the new user will use their current phone for less than 1 year, right? So that's the relevant. So find the probability that a random person that we choose out of the sample will use their phone for less than 1 year before buying a new one, and we assume that the variable is normally distributed. Okay. All right. So if this variable is normally distributed, it has a mean of 1.5 and a standard deviation of 0.25. So the center of the distribution is 1.5 and the standard deviation is 0.25. We are interested in knowing the probability that the random person that we pick will use their phone for less than 1 year. So this is, if this is 1.5, this is where 1 will be. 1 will be to the left of 1.5, and it's less, so we are interested in the area to the left of it. What is the probability that this person will use the phone for 1 year or less? So less is on the left hand side, so that's the question we are asking. Okay, so we can't find this area directly, so we have to apply the z transformation to it so that we can take this normal distribution and convert it into its standard normal form. So the z-score for x equal to 1, the transformation, we apply just the formula. So x is 1, mu is 1.5, sigma is 0.25. So 1 minus 1.5 over 0.25 is negative 2. Okay, so what I then do is basically go into my standard normal table that I already have, look for a value of negative 2 and look at the cumulative area, because it's the cumulative from the left up until negative 2. How much area do I get? That's 0.0228. Then that's the same area that the probability that x is less than 1. So this should be 1, sorry. The probability that x is less than 1 is 0.228. Okay. The way to interpret this number is basically, if I multiply this by 100%, that's 2.28%. So what this tells me is about 2.28% of cell phone users will keep their phones for less than 1 year before they spring for a new one, right? Given that the average is 1.5 and the standard deviation is 0.25, about 2% of people generally go on and buy a new phone within a year. Right? That's what it means. Okay. Some more examples. So, survey indicates that each trip to the supermarket, a shopper spends an average of 45 minutes. So we know the average is 45, the mean is 45. Standard deviation is 12. So we know the mean and the standard deviation. And we know that the length of time is also normally distributed and is measured by this variable x. Okay, so the amount of time a shopper spends inside the store is a normal distribution, and that's what x is measured. Okay, a shopper enters the store. Find the probability that the shopper will be in the store between 24 and 54 minutes. Okay. So we first start with the distribution itself. So the x distribution, the length of time spent shopping. So the mean is 45. We know that. The average is 45. The standard deviation is 12. We want to know, okay, and this is P here. It's not properly labeled. 54. Okay. We want to know what is the probability that a shopper who enters the store spends between 24 and 54 minutes inside the store. So we want to know the area in this region. Okay, that's basically the question. What is the probability that the shopper spends between 24 minutes and 54 minutes shopping in the store? Okay. Now the problem is, of course, that we can't find this area directly, so we need to make sure that we take these x values and transform them into their corresponding z values and then go to the standard normal table to find the areas. Okay, so let's start with 24. Right, so 24 is the value I'm converting minus the mean, which is 45, over the standard deviation, which is 12. So it's negative 1.75. Right, so that's what's represented here on the z-axis, that the value of 24 on the x-axis corresponds to value of negative 1.75 on the z. Okay. Similarly for 54, that's the other endpoint, so we need to convert that into a z-score as well. So the value is 54, the mean is 45, the standard deviation is 12, that corresponds to value of 0.75. So to ask the question, what is the probability that x is between 24 and 54, is basically the same as asking the question, what is the probability that the z-score is between negative 1.75 and 0.75. Okay. To answer this question, what would I do? So I want to find the area between two z-scores. So first I'd go into the z table and look for 0.75 and find the area which is closest to it. So the area which is closest to 0.7, the area which corresponds to 0.75 in my z table is 0.7734. So the area to the left of 0.75 is 0.7734. Then I go into the z table again, look for negative 1.75 and the area associated with it, it's negative 0.0401. So the area to the left of negative 1.75 is 0.0401. So the area in between these two z-scores is the difference between these two areas. This is the entire area. This is the area to the left here. So the difference tells me this area. Okay. So the area, the difference here is 0.7734 minus 0.0401. So the area in between those two z-scores is 0.733. Or if you want to interpret this number, it says that 73.3% of shoppers will spend between 24 and 54 minutes shopping in that supermarket, given what the distribution looks like. Okay. All right. Similarly, here's a second example. Find the probability now that a random shopper will be in the store more than 39 minutes. Same mean, same standard deviation, same distribution, everything is the same. But the crucial thing here is that it's more, and then it's more than 39 minutes. Okay. So we start with the same distribution. So 45, that's the mean. So we know the distribution's bell-shaped. So we are interested in knowing 39, but we are interested in knowing what is the probability that they spend more than 39 minutes in the store. So that's the area to its right. We are interested in knowing this area here. Okay. So the probability that x is greater than 39 is the area to the right of 39. We can't find this area directly. So what do? We first transform it into its z-score. So the value is 39. So we start with x, 39. Mean is 45, standard deviation is 12, so that's negative 0.5. So value of 39 on the z-axis for this distribution corresponds to a z-score of negative 0.5. Okay. So far so good. We just applied the z-score transformation to it. Now the question is, okay, so I'm interested in the area to the right of the z-score, but if I go into my table and look up the value negative 0.5 in my table, it's going to tell me cumulative area, or it's going to tell me area to the left. So if I go to my z table, into my standard normal table, and look at this value negative 0.5, it corresponds with the area of 0.3085. So the area to the left is 0.3085, which means that the area to the right here would be 1 minus the area to the left. So the probability that x is greater than 39 is, first of all, the probability that z will be greater than negative 0.5, which is 1, which is the total area, minus the area to the left. So the area in between there is 0.6915. So the way to interpret this number is that the probability that the shopper will spend more than 39 minutes shopping in the store is about 69.15%. Or a second interpretation of that same number is that about 69.15% of all shoppers spend more than 39 minutes shopping in the store. Okay? All right. So just get comfortable using the Z table. It's on Blackboard. I posted the file. It's also in the appendix of the textbook. It's also available online, so you can always just Google standard normal table and it'll show up, and you can use that as well. Okay. So you can use this to answer more interesting questions like, okay, so if 200 shoppers enter the store, how many shoppers would you expect to be in the store more than 39 minutes? Right? So we know that the probability that x is greater than 39 is 0.6915, which is to say 69.15% of all shoppers who enter the store are still there 39 minutes later. So if 200 shoppers enter the store, 69.15% of the 200 shoppers are still going to be in the store 39 minutes later. So 200 times 0.6915, so that's 200 shoppers, 69.15% of these 200 shoppers. So it's about 138 odd shoppers are going to still be in the store 39 minutes after they show up. Okay. So just a few quick examples on what kind of questions you can answer and how to basically find probabilities using the standard normal table. Okay. So the last thing we'll do for this week is to go the other way, right? So in the last section in 5.2, we knew x, we wanted to find the probability, right? Which is to say we wanted to find area. This is the same as trying to, oh man, okay, this is horrendous. Okay, so we knew x, we were interested in finding an area under the curve for x. So that was the probability. And the way we could do that was first take x, convert it into a z-score, and then use that to find the probability, right? So that's what we did in 5.2. In 5.3, we jump the other way around. What happens if I have a probability in mind or an area in mind? How would I find the corresponding x value? Again, I jump through two hoops. If I know the probability, first I find what z value is associated with it. Once I know that z value, I can find the x value. Okay. All right. So let's see. How would we do this? Okay. So suppose I have a situation like this. I want to know what z-score corresponds with an area with a cumulative area of 0.3632. Okay. So the area to the left of this z-score is going to be 0.3632. And I want to know what is this z-score for which the area to its left is 0.3632. Okay. So what would I do? I just reverse the process, right? So what I do is that I go into my standard normal table, start looking through it. I don't look at these things just yet. I'm trying to locate the area inside the body because the body of the table is going to tell me what the area is. So I start looking through it. Oh, it's 0.35257, and here I found it, 0.3632. So if you don't find the exact area, you find the closest one that you can find and use the z-value attached to it. So in this case, obviously I set it up so I could find the exact area. So the area is 0.3632, and then I read off the z-score which generates that area, which is negative 0.35, right? So a z-score of negative 0.35 will have an area to its left of 0.3632. So I basically reversed the process. In 5.2, I was looking at the z-score first. So I was locating the z-score and then reading of the corresponding area. In this case, first I find the area and then read of the corresponding z-score. Okay. All right. Similar situation again. So suppose I want to find the z-score that has 10.75% of the distribution's area to its right. I want to find the z-score such that the area on its right is 10.75% or 0.1075. 10.75 over 100 is 0.1075. Now, going back to the basics, the first thing to know is that the standard normal table is only going to report areas to the left. It's going to tell me cumulative area. So I know area to the right, but that doesn't mean no good. I need to find the area to the left before I can use the table. So if I know the area to be to the right to be 0.1075, then the area to the left is 1 minus the area to the right. So 1 minus the area to the right is 0.8925. So that tells me that this is the right number for me to go look for in the body of the standard normal table. So I go to my table and then I start looking through it, right? I have to comb through it. Once you do it a few times, you'll be able to rapidly go quickly here. But you're looking through all these numbers, so 0.8686, that's not high enough, and then you keep going, and then you find 0.8925, and then you can read off the corresponding z-score as 1.24. Okay. So if you know the area, you can always get the z-score back. Right? So that's the first loop to jump through. Okay. Again, similar situation. P5 represents the fifth percentile. Remember, percentiles tell me how much area, what part of the distribution is below that number. So the fifth percentile tells me that the area to the left is of this is about 0.05. Right? 5%. Fifth percentile is that 5% of the data is to the left of that z-score. So I just go into the table and try to look for 0.05. So if I go into the table, sometimes I end up in these weird situations where 0.05, I can't find it in the table, but it's exactly halfway between 0.0495 and 0.0505. Usually I would end up choosing the closest one. On the exam, I don't really care. You can just choose the closest one. In this case, you can't really make a choice because it's 0.0495 and 0.0505 are equally far from 0.05. Right? The z-score for this is negative 1.65. The z-score here is negative 1.64. So I just average out these two z-scores and use them. Right? I use the halfway point between negative 1.64 and negative 1.65. So the z-score here, which corresponds with an area to the left of 0.05, is negative 1.645. Okay. This fifth percentile number and the z-score attached to it will become very, very, very important quite quickly. So it's one of those numbers, if you do statistics, you know it off the top of your head. You don't need a table, you don't need to ask anyone, you just know it off the top of your head, because it's crucial once we move further into the material as to why this is very important, particularly significant, I wouldn't say important, particularly significant z-score, okay, of 1.645. So negative 1.645 is the z-score, which tells me that the area to the left of that is 0.05, or 5% of the area is there to the left of negative 1.645. Okay, so that's the first jump. So if I know the area, I can find the z-score. If I can find the z-score, I can retrieve the x value, right? That's the second jump. So in the last section, we knew the x value, we wanted the probability, so we took the x value, converted into z, and then used that z to find the area, which was the probability. In this section, we know the probability, so first we find the z which is attached to that probability, and once we know z, we can find x just using this formula here, right? Let me see if I can. Okay, so this is the formula basically which I use. So once I know what the z value is, I can retrieve the x value which is attached with, right? So that's the x value which is attached with. So it's just the mean plus z times sigma. It's just a reframing of the z-score formula. So z was x minus mu over sigma x. So if you just do some transformations, I mean, it's not particularly important, but the thing is to see that x is mu plus z sigma. Okay. All right. The question is, how do I use these things? So a vet records the weights of cats treated at a clinic. The weights are normally distributed. The average, the mean is 9 pounds. Standard deviation is 2 pounds. Find the weights of x corresponding to z-scores of 1.96, negative 0.44, and 0. Right? Just applying the formula. Right? Use the formula. So when z is 1.96, then x will be mu, which is given to be 9 pounds, plus the z, which is 1.96 in this case, times the sigma. Sigma in this case is 2 pounds. So it's 9 plus 1.696 times 2, or 12.92. Yeah. So when z is negative 0.44, then x will be 9 plus negative 0.4 is the z value, and 2 is the standard deviation, and so on. Okay. So this is just how to use the formula and where to plug in what. Okay. But that's not that important. The more important thing is to figure out how to use this information. Right? All right. So let's look at an example for this. So scores for the California piece, there's a test. They're normally distributed. The average score is 50 and the standard deviation is 10. Okay. So the hiring criteria that the agency establishes is that it will only hire people who take these tests who score in the top 10% of the test. Okay. So I know that the test scores are normally distributed, right? I know the test scores are normally distributed. So I want to ask the question, where the mean is 50 and the standard deviation is 10. I want to ask the question, what score do I need to get to be in the top 10% of this distribution? To be at least at 10% or more? What is the minimum cutoff score that I can get so I can be in the top 10% of the test takers and then get the job? Okay. So I know the distribution. I know I want to be in the top 10%, which is to say I want to know what value of x, what test score do I need so I can be in the top 10%. Okay. So to find this value of x, first I need to find the z which is attached to 10%, right? So the area to the right here of the z score is 10%, or 10% is 0.1. That's not useful for me. I can't use the table because the table always tells me areas to the left. So the area to the left of the z-score is 1 minus 0.1 or 0.9. Okay, so I would go into my standard normal table and I would find the z-score, which has a cumulative area of 0.9, and it turns out that z-score is 1.28. Okay, so from the standard normal table, the area closest to 0.9, so I look through the body of that table, and the area which is closest to 0.9, I find is 0.8997. So I use the z-score which is attached to this number because it's close enough, it's a good enough approximation, and so the z-score that I use is 1.28. So I know the area to the right. So first I found the area to its left, then I found the z-score. Once I have the z-score, then finding x is straightforward. So x is mu plus z sigma. So mu is 50, that was given. Sigma is 10, that was given. And I found z to be 1.28. Okay, so z is 1.28, so it's mu plus z sigma. So mu x is 50, mu is z is 1.28, sigma is 10. So the x value which corresponds to the top 10%, the cutoff value for the top 10% on this test is about 62.8 or about 63. So you need to get at least 63, a score of 63 or more on this test to be hired for this position. Okay, this is a situation where we knew the area that we were after. So first we found the z-score, and once we found the z-score, we plug it back into this formula, and then we can find the x value which is associated with that z-score. We're basically reversing the entire process. Okay,